magnetic field of magnitude 0.50 Tesla is directly perpendicular to the plane of a rectangular loop having dimensions 8.0 centimeters by 12 centimeters. Find the magnetic flux through the loop. So they say that the magnetic field is perpendicular to the plane. So what we know? Well, in this case, we know that we have a plane here. And then we have a magnetic field that is perpendicular to this plane. So this is my magnetic field. So this is my magnetic field. So the angle between the normal to the plane and the magnetic field, the angle theta, is in this case 0 degree. So we know that the formula to calculate the magnetic flux is VA cosine of theta, which comes from B perpendicular times A. And B perpendicular would be V cosine of theta. So we get that this is VA cosine of theta. Now, since theta is equals to 90 degrees, the cosine of 90 degrees, if you evaluate in your calculator, is going to be 1. So theta B is then equals to VA. So the magnetic flux to this plane is equal to B times A. Now, what is the area? They say the area is 8 centimeters by 12 centimeters. It's a rectangular loop. But we need to convert to calculate the area, the 8 centimeters into meters. So 8 centimeters into meters is 8.0 times 10 to the negative 2 meters. And 12 centimeters would be 12 times 10 to the negative 2 meters. So when we multiply, we will have an area that is length times width. There is then 12 times 10 to the negative 2 meters times 8.0 times 10 to the negative 2 meters equals to 96 times 10 to the negative 4 meters squared. This is, in this case, the area. So for this area, we can now calculate the magnetic flux that passes through that area. It's B times A. B is 0.50 Tesla, and the area there is 96 times 10 to the negative 4 meters squared, and this gives us 48 times 10 to the negative 4 Tesla meters squared. Tesla meters squared is Weber, so we can say that the magnetic flux here is 48 times 10 to the negative 4 Weber, and is the unit in the international system for magnetic flux. And then you can rewrite this 48 times 10 to the negative 4 in scientific notation as 4.8 times 10 to the negative 3 Weber. So what is in this case? What is in this case? The magnetic flux to the given area is 4.8 times 10 to the negative 3 meters. So this exercise was very easy because in this exercise, you know, we had that the angle was 90 degrees. So we have the maximum magnetic flux to that area, and that maximum magnetic flux to the area was 4.8 times 10 to the negative 2 meters. So this is just one of the simplest cases, one of the simplest problems. And in this problem, well, to highlight this formula that say that the magnetic flux through E is PA cosine of theta. And when they say directed perpendicular to the plane, now we know that theta is 0 degree, the cosine of 0 degree is 1, and then the formula to calculate the magnetic flux becomes V times A. So all this is just from this statement, right, or from this sentence that say that the magnetic field is perpendicular to the plane, right? So all this analysis is derived from this expression or this sentence that say that is directed perpendicular to the plane. Any questions so far? Let's see here a second example. They say that the figure below shows 3 edge views of a square loop with sides of length L equals 0.250 meters in a magnetic field of magnitude 2 Tesla. So they say calculate the magnetic flux to the loop first. When the loop is oriented perpendicular to the magnetic field, when the loop is oriented 60 degrees from the magnetic field, and when the loop is parallel to the magnetic field. Well, first, this could be a little bit confusing because they are representing like a circular loop, but they really say here, you know, that is on a square loop with sides of length 0.250 meters. So we have to be careful in this problem because they say it's on a square loop with sides of length 0.250 meters. So the first I'm going to do is to calculate the area of the loop before doing any other thing. So the area of the loop, as it's on a square loop, would be the square of the side. S is the side of the loop, and it's equal to 0.250 meters. So the area of the loop, which is S squared, is 0.250 meters squared. When you calculate that, you will get 0.0625 meters squared, which is the same as 6.25. That's 6.25 times 10 to the negative 2 meters squared in scientific notation. Now, what they say in the first scenario. In the first scenario, they say that we have that the loop is perpendicular to the magnetic field. So we have the loop here. We have the loop here. And we have the magnetic field perpendicular to the loop. So in red, I will represent my magnetic field. Which is perpendicular to the loop. when the magnetic field is perpendicular to the loop, then remember that the normal to the area of the loop is parallel to this magnetic field. So in this case, the angle theta is 0 degree. So when I now say that the magnetic flux is VA cosine of theta, since theta is 0 degree, the cosine of 0 degree is 1. So the magnetic flux through the loop will be VA. So it will be the 2.00 Tesla times the 6.25 times 10 to the negative 2 meters squared. So the magnetic flux through the loop would be, when you calculate that, 0.125 Tesla meters squared, which is the same as 0.125 Weber. 0.125 Weber. This is when the loop and the magnetic field are perpendicular. Now, we have a second case here that could be confusing. Why? Because again, we have the loop. And now I say, the magnetic flux through the loop is oriented 60 degrees, from the magnetic field. 60 degrees from the magnetic field. So calculate the magnetic flux through the loop, and the loop is oriented 60 degrees from the magnetic field. So the angle between the loop and the magnetic field is 60 degrees. And there is where we can be easily confused. Because this is 60 degrees. This angle between the magnetic field and the loop, and the area of the loop. Now, remember that the angle theta is not between the loop and the magnetic field. The angle theta is the angle between the normal to the area of the loop and the magnetic field. So I have a normal vector here. And the angle theta is really the angle between B, the magnetic field line, and this normal. So the angle theta is not 60. The angle theta is 30 degrees. Is the complement of 60. Is the complement of 60. So if 60 is the angle between the area of the loop and the magnetic field, then the angle between the perpendicular to the area of the loop and the magnetic field, which is theta, is the complement of 60, is 30 degrees. So that could be confusing, because if you use 60 degrees to calculate the magnetic flux here, your answer will be wrong. So you have to use 30 degrees. 30 degrees, because theta is the angle between magnetic field and the normal to the plane of the loop. So in this case, I have to use the same equation. Magnetic flux is equal to VA cosine of theta. Now, it's going to be be 2 Teslas times the area, 6.25 times 10 to the negative 2 meters squared times the cosine of 30 degrees. So when you calculate the magnetic flux now, this would be 0.108 Tesla meters squared, which is the same as 0.108 well, 0.108 well. Now, the third case, they say that the loop is oriented parallel to the magnetic field. The loop is oriented parallel to the magnetic field. So this is my loop. And then here in red, I have my magnetic field. What happens here? The normal to the loop is this vector. And the angle theta, that is the angle between the normal to the loop and the magnetic field, is 90 degrees. The cosine of 90 degrees is 0. So when you say that the magnetic flux here is VA cosine of theta, the magnetic flux here is VA cosine of theta. Since cosine of theta is 0, all this expression turns 0. So the magnetic flux to this loop is going to be 0. 0 where? So there you have the three cases. The case where the magnetic field and the loop were perpendicular, that was where we got the maximum value of magnetic flux. The case where the angle between the loop and the magnetic field was 60 degrees, so the angle between the normal to the loop and the magnetic field was 30 degrees. And now we got a value, of course, lower than the maximum value. That is when it's perpendicular. And we have a third case, that is when the angle between the loop and the magnetic field is, in this case, 0 degree. So the angle between the normal and the magnetic field is 90 degree, and the cosine of 90 is 0. So the magnetic flux in this case is just 0. So this is a very interesting exercise because it combines, three different scenarios. So any questions so far? I have another exercise for you here. Before taking a break, look at this next exercise. They say, a long straight wire lies in the plane of a circular coil with a radius of 0.010 meters. The wire carries a current of 2 amperes and is placed along the diameter of the coil. So what is the net flux through the coil? B, if the wire passes through the center of the coil and is perpendicular to the plane of the coil, what is the net flux through the coil? So again, we're going to find the magnetic flux through the coil, right? Now, we have a long straight wire that lies on the plane first of the circular coil with radius 0.010 meters. So basically, in my first case, here is my coil. And then I will have this wire that passed through the center. It's just along the diameter of the coil. They said the coil have a radius of 0.010 meters. And then they say that the wire carries a current of 2 amperes. Now, they don't say in what direction is this current, so I would be assuming the current points over, like this. Now, how is the magnetic field that you have around this current carrying wire? Well, if you use the right-hand rule, and you just put your thumb in the direction of the current eye, and you try to wrap your fingers around the wire, you will see that the magnetic field to the left of the wire is leaving the plane. To the left of the wire, the magnetic field is leaving the plane for this direction of the current that we are assuming. But to the right of the wire, the magnetic field is entering to the plane of the wire. Just like this. Now, if you analyze the number of magnetic field lines to the left of the wire leaving the plane, and the number of magnetic field lines to the right of the wire leaving the plane are the same. Because this magnetic field, right, have the same intensity to the left and to the right of the wire as you are at the same distance from the wire. So basically, in this half to the left of the wire, you have one magnetic flux, that of course is due to the magnetic field leaving the plane. So just that magnetic flux, there is a BA cosine of theta. Let's say that the normal is leaving the plane. So let's say that the normal to the plane of the wire, of the loop, right, is leaving the plane. So the angle in this case is 0. So this would be VA cosine of 0 degree, which is going to be VA. But to the right of the wire, the angle is 180 degree. So this would be VA cosine of 180 degree, because the normal vector and the vector B to the left of the wire, the current carrying wire, are parallel. But to the right of the current carrying wire, the vector end and the magnetic field are anti-parallel. So they make an angle of 180 degrees. They have opposite directions. The cosine of 180 degree, the cosine of 180 degree is -1. So the magnetic flux to the right would be negative VA. So to the left and to the right, you have the same magnetic flux, but with opposite signs. So the net magnetic flux would be VA minus VA, and it would be 0. So really, when you find the net flux to the coil, the net flux to the coil here is 0. Now, let's say the second example, the second case, the second scenario. You have your coil. But now the wire is perpendicular to the plane of the coil. So it's concentric with the plane of the coil. So I would be representing the wire here. And I will put this cross, because this cross represents the direction of the current. So I have a current entering into the plane. So this is the loop. This is the wire with a current that enters to the plane of the screen. Right? Now what happens? When you analyze the field surrounding that wire, the field, the magnetic field that surrounds the wire is circular, like this. So the magnetic field, using the right-hand rule, is clockwise. If the current enters into the plane, the magnetic field is clockwise, and the magnetic field is parallel to the plane of the loop. Now, the normal to the plane of the loop, the vector normal, is perpendicular to the magnetic field lines, because the magnetic field lines are in the same plane of the wire. So since the normal is perpendicular to the magnetic field, the angle theta is 90 degrees. And we know that the cosine of 90 degrees 0. So here, the magnetic flux, that is VA cosine of 90 degrees, since this is 0, this magnetic flux will be also 0. So in both cases, the magnetic flux is equal to 0. In the first case, the magnetic flux is 0, the net magnetic flux is 0, because the magnetic flux to the left of the wire and the magnetic flux to the right of the wire, are the same, but are opposite direction. And then later, in the second case, the magnetic flux is 0, because the magnetic field lines are parallel to the loop, and perpendicular to the normal. So that's why in this case, you have that it's also 0, because the cosine of 90 is also 0. So the whole expression becomes 0 in this case. This is one of the most interesting problems, that I have seen in this case, because when they start using this idea of the net magnetic flux and they locate the wire exactly on the diameter in the first case, now we have the same magnetic flux leaving the plane that enters to the plane. So the net flux is just 0. If they move the wire, the current carrying wire, either to the right or to the left of that diameter, then the net magnetic flux will be different of 0. If they move this wire either a little bit to the left, like this, or a little bit to the right, sorry, it would be, in this case, the magnetic flux. The net magnetic flux will be different of 0, because you will have more lines leaving the plane that enter into the plane, or more magnetic lines enter into the plane that leave the plane, depending, on the position of the wire. So in that case, the net value will be different of 0. They say that 3 loops of wire move near along a straight wire and carry the current, as is shown here below. What is the direction of the induced current, if any, in loop A, loop B, and loop C, right? Well, first, we know that due to this current I, we have a magnetic field surrounding this wire, carrying the current I. So how is going to be that magnetic field? Well, if you apply the right-hand rule, this magnetic field would be leaving the plane here to the left, and it would enter to the plane to the right. This is due to the current I. Now, what happens with this loop A? The loop A is moving over. It's moving in the direction of the current. Now, the intensity of the magnetic field decreases. So the value of V decreases as you move from the wire you know, to a point that is just more far away from this wire. So as you move away from the wire, the magnetic field decreases, right? Now, when you move along the wire, the magnetic field doesn't change. So for this loop A, the magnetic field that passed through the loop A doesn't change in magnitude. It's the same magnetic field. And we know that we have a current induced only if there is a change in the magnetic field. Okay? So for loop A, we have that the current induced would be 0. Why? Because as A move along the wire, the variation of magnetic flux is 0, right? Why? Because as it's moving at the same distance, as it's moving, keeping the same distance from the wire, B doesn't change. B, magnetic field that is passing through the loop doesn't change. So when this loop A is moving along the wire, it always has the same magnetic field passing through the loop. So they have, a variation in magnetic flux that is 0, and for the 0 variation in magnetic flux, we have no current in this. Now, look at this other. For loop B, this is our loop B. As loop B is moving away from the wire, this magnetic field that is passing through loop B will decrease in magnitude, right? Because as I said, as you move away from the wire radially, there is a decrease in the magnetic field. So it's needed a current here that induce, based on Lenz law, that induce a magnetic field in the same direction that the magnetic field, that the loop B have as its original position, in order to increase the magnetic field through the loop B, right? So since the magnetic field through loop B is decreasing as you move, right? So since the magnetic field through loop B is decreasing as you move away from the wire, you need to counteract that decrease, inducing a current that will create a magnetic field that oppose that decrease. So that would be in the same direction that the magnetic field we have over here. So what that means, that the current that we're inducing now here is going to be a current counterclockwise like this. Why? Because if you apply the right-hand rule, now in all this area inside, you have a magnetic field that is leaving the plane. So the magnetic field due to this straight wire decreases. So that induces a current that opposed to that decrease, creating a magnetic field inside that increase. Or outside this loop, you have that the magnetic field enters into the plane of the wire, of the computer side. So the current that needs to be induced here, based on Lenz law, to counteract the decrease, needs to be counterclockwise, because when it's counterclockwise, we have then here inside the loop a magnetic field in the same direction that the magnetic field due to the straight wire. Now, let's see what happened in this case for loop B. So the loop B, the loop C. Loop C is to the right of the current carrying wire, and it's moving to the right. So it's moving also away from the wire. So the magnetic field here, the magnetic field through the loop is decreasing. Because remember, as you move away from the wire, the magnetic field decreases. So there would be a change in magnetic field, and that is going to induce a current. But that current that will be induced needs to counteract the decrease in magnetic field. It needs to counteract the decrease in magnetic field. The intensity of the magnetic field crossing across the plane of the loop. So the current that will be induced will be clockwise. It will be clockwise. Because when the current is clockwise, now it will enter to the plane here in the inner part of the loop. So basically, it's going to have the same direction that the magnetic field due to I, which is decreasing. So that reinforces that magnetic field. So it opposes to the decrease of the magnetic field due to the straight current carrying wire. Outside the loop, due to this current, now it's just leaving the plane, the magnetic field. So remember, that what I am representing here in red is the magnetic field. Okay? And of course, the arrows are for the current. So this is what happens in this case. So that you have a decreasing magnetic field as loop B and loop C move away from the wire, there is a change in the magnetic flux which induces a current in the loops, but that current in the loops will induce a magnetic field that will oppose what? To the change. And the change was a decrease, then the current induced generates a magnetic field that counteracts that decrease. This is another very interesting, problem where we don't solve anything numerically, but we have to analyze, how we change the magnetic field and in what direction will be the current when we move the loop. Now, may I change slide? So let's see the next exercise. Next exercise say this. Inductive charging is used to wirelessly charge electronic devices, ranging from toothbrushes to cell phones. Suppose the base unit of an inductive charger produces a 1 times 10 to the negative 3 Tesla magnetic field. Varying this magnetic field magnitude changes the flux through a 15-term circular loop in the device, creating an electromotive force that charges its pattern. Suppose the loop area is 3 times 10 to the negative 4 meters squared, and the induced electromotive force has an average magnitude of 5 volts. Calculate the time required for the magnetic field to decrease to 0 from its maximum value. To decrease to 0 from its maximum value. Well, let's see first what it is brought about. What formula we can use, what is given, what is unknown. So what we have here, we have a magnetic field that have an intensity of 1.00 times 10 to the negative 3 Tesla. Right? Now, we have a number of terms. There is 15 terms. So, N is what represents the number of terms. And this is 15 terms. So that loop have 15 terms. There are 15 loops together, right? Now, what else they say? They say that the area of the loop, so A, is 3.00 times 10 to the negative 4 meters squared. And there is an induced electromotive force. There is 5 volts. 5 volts. Or these are known. What is unknown here? They ask you to calculate the time, delta t, that requires the field to decrease to 0 from its maximum value. So the maximum value is this value of 1.00 times 10 to the negative 3 Tesla. And the minimum value here would be 0 Tesla, right? So I will call this maximum value the initial magnetic field. And I will call this minimum value 0 Tesla the final magnetic field. Because they say calculate the time required for the magnetic field to decrease to 0 from maximum. Decrease to 0 from its maximum value. So the initial value is the maximum and the final value is 0. Now, what we know, what equation relates all the physical quantities? We know that the Faraday law says that the electromotive force that is induced, is equal to negative n delta phi v over delta t. Delta phi v over delta t. Now, what is delta phi v? So what is delta? What is the variation of magnetic field? Is the magnetic field, sorry, the magnetic flux, variation of magnetic flux, the magnetic flux final minus the magnetic flux initial. This is the magnetic flux final minus the magnetic flux initial. What is the magnetic flux final? Is B final times the area, so the intensity of magnetic field final times the area, minus what is the magnetic flux initial? The initial minus what is the magnetic flux initial? The initial magnetic field times the area. But we found that B final is 0 Tesla. So if B final is 0 Tesla, this is 0. So the variation of magnetic flux will be minus B initial times the area. So I can substitute now this minus B initial times the area here, because this is delta phi B. So I can say that the induced electromotive force is minus N times minus B initial times the area divided by delta T. What I want to calculate? What I want to calculate is delta T. So solving for delta T will be the induced electromotive force divided by, delta T will be minus N. Because delta T, E times delta T is minus N times minus BI B sub IA. So now when you solve for delta T is negative times negative will be positive, and B sub IA over the induced electromotive force. So this would be 15 terms times the initial magnetic field, which is B maximum, that is 1.00 times 10 to a negative 3 Tesla, times the area, that we know there is 3.00 times 10 to the negative 4. Sorry, let me. Sorry. Let me do this again here below, because I don't have enough space. So this would be, N is 15 terms times B sub I, that is 1.00 times 10 to a negative 3 Tesla, times the area, there is 3.00 times 10 to a negative 4 meters squared, divided by the electromotive force induced, which is 5 volts. So this delta T, when you calculate it now, it would be 9.00 times 10 to the negative 7 seconds. Now, 9.00 times 10 to the negative 7 seconds is the same that 0.90 times 10 to the negative 6 seconds, and 10 to the negative 6 is micro, so it's 0.90 microseconds. So that would be the time. So this is microseconds. So in this case, the time needed to have that variation is 0.90 microseconds. So of course, it's a very, very small time. Any questions so far? You know, this part is just really difficult to understand. You know, there is a couple of equations, basically, that are the equations we use, all right, in this part. Just a couple of equations, and all the problems are solved with that couple of equations. When there's a question like those questions where I was asking, like, you know, the question about how the loop is moving, so that is just an application. So it turns just more difficult. But when it's just about using the equations that we have here are very, very simple. The Faraday law is a very simple equation involving a couple of terms. Magnetic flux is a very simple equation also that involves some factors, you know, but it's not too difficult really. Let's see this other problem, which is super, super interesting also. It's basically again about, you know, how it's moving or how it's just the current induced when you move a magnet again. So look at this problem, which is really interesting. They say, if our magnet is positioned near a coil of wire, as is just shown below. So what is the direction of the current in the resistor when the magnet is moving? So they say when it's moving to the left, and later when it's moving to the right. Well, first, let's try to see, you know, how is in this case the magnetic field of this magnet. The magnetic field of this magnet go from north to south. It go from north to south, right? Like this. This is the magnetic field of this magnet. Now, as you're moving this magnet to the left, right? As you're moving it to the left, what is happening? The magnetic field, you know, through this coil, the magnetic field to this coil is going to decrease. So now, the current that is going to be induced needs to try to oppose to that. So we need a current now that will oppose to that decrease. So we need a current that will generate a field that will be in the same direction. We need a current that will generate a field, that will be in this same direction. So how is going to be the field? Like this. Now, how needs to be the current? In what direction needs to be the current that generates such a field? The current that generates such a field. Now, using the right-hand rule, as you have a coil there, you know, you will have to, with your fingers, follow the direction of the current. Your thumb will indicate the direction of the field. So the current you need to have that field to the right needs to be a current that goes in this direction here, because when it now follow this wire, you know, it goes like this. This is how your current is going. So get your four fingers, try to wrap, the coil. And you will see how when you wrap, your coil, the magnetic field points in the direction you want, that is to the right. Okay? The magnetic field is in the direction that you want. And it's this. So as this is moving away, this magnetic field is decreasing. As the magnet moves away to the left, this magnetic field is decreasing. So you need to counteract that decrease. So the current that will be induced is going to counteract that decrease. And how can counteract that decrease? Just being inducing current, that induces a magnetic field that just goes in the direction of the magnetic field of the magnet, right? So that current is just like this. So this is the magnetic field, this is the current wrapping, and I wrap, this kind of solenoid or coil, with multiple turns. So this is the direction of the current in this case. Let's see the other case. Let's see now the other case. So let me erase this. Now, in the second case, again, this is the magnetic field into the magnet. Now, the magnet is, this is the magnetic field into the magnet. Now, the magnet is moving to the right. Now, the magnet is moving to the right. So the field is increasing. So the magnetic field is increasing. So now, the direction of the current that will be induced in the resistor is a current that will oppose to that increase. So it's a current that is going to generate a magnetic field that opposes to that increase. So how needs to be, in what direction needs to be the magnetic field that opposes the increase? In this direction. So now I want a magnetic field in that direction to oppose increase. Now, if the magnetic field is in that direction, use the right hand rule, wrap your four fingers around, the solenoid or coil, or wire that you have here, and then your thumb is in the direction of the magnetic field that current needs to induce, and you will see how the current now needs to follow this other path. So now the current here is like this. So this is how the current, this is the direction required for the current to now induce on a magnetic field that will counteract the increase in magnetic field when you move the magnet toward the coil or the solenoid, or toward the circuit with the resistor that you have over there. So this is, how is the new current. So this is the kind of analysis that you have to do. So again, it's one more exercise where what are we doing is just basically applying, what we know about Faraday's law and Lenz's law. Look at this other case. Now, they say a pickup truck has a width of 79.8 inches. It is traveling north at 37 meters per second to a magnetic field, with vertical component of 35 microtesla. What magnitude electromotive force is induced between the driver and passenger sides of the truck? So what we have here, well, basically, you have a truck that will look like this. You're the passenger, the driver, and what you know that you have a distance, of 79.8 inches, basically. As is the width of the truck between the driver and the passenger. Now, what happens? I will represent this truck with a top view, and I will represent it basically like a bar. So I will have like a bar here. The truck is made of metal, so it's like a metallic bar that is moving north like this. But there is a vertical magnetic field of 35 microtesla. So you have a vertical magnetic field like this, so perpendicular to the direction of the motion of this truck. This is your magnetic field. This magnetic field has 35 microtesla of intensity. The velocity of the truck is 37 meters per second. What they want to know, what is the induced electromotive force? Now, what we know from previous slides, when I was explaining, basically, I called that part emotional electromotive force. We know that the equation to calculate the electromotive force in the emotional electromotive force is BLB. So intensity of the field times the length of the bar that is moving times the velocity of that bar. So this is the equation to calculate this electromotive force. The induced electromotive force between the driver and the passenger. Now, we know that this length is in inches, so we can convert the inches into meters. So we have 79.8 inches times, now look at this, we know that we have 0.0254 meters per inches. Meters per inch. Why? Because it's 2.54 centimeters per inch. So 2.54 centimeters is 0.0254 meters per inch. Like that, you can convert these inches into meters, and you will get in meters 2.03 meters. So once you have this length in meters, now you can substitute and calculate induced electromotive force. That is the 35 microtesla, so it's 35 times 10 to the negative 6 Tesla, times the length, that is 2.03 meters, times the velocity, that is 37 meters per second. And when you calculate all that, it gives you 2,630 times 10 to the negative 6 volts, which is going to be 2.63 times 10 to the negative 3 volts, which is 2.63 millivolts. So just only, and look at how interesting is this, right? So just only because the car is moving to a magnetic field, and remember that we all are moving to a magnetic field because we have the magnetic field of the Earth, right? So we all have the magnetic field of the Earth acting around us, right? So now you are in a car. The car is made usually of metal, right? Which is a conductor of electricity. Okay? Of steel or aluminum, different parts, right? Which is conductor of electricity. Yeah? So now what happened with this? There will be an electromotive force induced just because this car is moving through a magnetic field. So when we say motional electromotive force, is you have a body that is moving with some velocity to a magnetic field, and due to this motion to the magnetic field, there will be an induction of electromotive force. There will be an induction of voltage. There will be now a difference of voltage of 2.63 millivolts between the passenger and the driver. Between the passenger and the driver. Let's see one more problem. And then with this problem, we're going to stop the class after this problem so we can just, I can print then the lab and we can then start doing the lab. So look at this other problem. They say, consider the arrangement below where the resistance is 6 ohms, the length is 1.20 meters, and B is equal to 2.50 Tesla. So the magnetic field is 2.50 Tesla. At what constant speed should the bar be moved to produce a current of 1 ampere in the resistor? So there is one resistor here. And then at what speed this needs to move to produce a current of 1 ampere in the resistor? What power is delivered to the resistor? What else? What magnetic force is exerted on the moving bar? And what instantaneous power is delivered by the applied force on the moving bar? So the first is at what constant speed should the bar move to produce a current of 1 ampere in the resistor? So well, which are the known? We have the resistance of the resistor. There is 6 ohms. What else? We have the length, of this metallic bar. That is what is moving to the force applied. So it's what causes a change, in the magnetic flux, which is 1.20 meters. We have a magnetic field with intensity 2.50 Tesla, and we want to produce a current of 1 ampere in that resistor. What is unknown? We have multiple unknowns. In the first part, the unknown is the speed. In the second part, the power delivered by the resistor. The power delivered by the resistor. In the third part, the magnetic force. And in the last part, the instantaneous power there is delivered by the force applied. These are the unknowns. Now, how we can calculate, this constant speed? Well, remember that current to the resistor would be the electromotive force divided by the resistance of the resistor. So whatever current we have here would be the quotient of the electromotive force divided by the resistance of the resistor. But we know that for a moving electromotive force, we have here that this is the intensity of the field. The electromotive force is the intensity of the field times the length times the speed. All this divided by the resistance of the resistor. So this is the same formula that I used in the previous exercise. Induced electromotive force equals intensity of the field times length times speed. Now, what we have to do, we have to solve for speed. So if I have I equals BLV over R, if I multiply I times R, I get BLV here. If I solve for V, I get that IR over the intensity of the field times the length is equal to the speed. So we can calculate the speed like that. So now, substituting, you say that your speed would be 1 ampere times the resistance, there is 6 ohms, divided by the intensity of the field, that is 2.50 Tesla, times the length, that is 1.20 meters. And that speed would be, when you calculate that, 2.0 meters per second. So, and a speed, of the bar moving, well, in this case, in the direction of the applied force, with a speed of the bar of 2 meters per second, we will have the current of 1 ampere that will be passing to the resistor. Now, in the second part, they say what is the power dissipated to the resistor. Well, remember that power is the square of the current times the resistance of the resistor. So if the current is 1 ampere squared times the resistance of the resistor, that is 6 ohms, the power dissipated by the resistor would be 1 squared is 1 times 66, 6 watts. 6 watts. That is the power that is dissipated by the resistor. Now, later, they ask you to calculate the magnetic force. The magnetic force will be equal to the intensity of the field times the current times the length. Like that, you can calculate the magnetic force. This magnetic force will oppose to the force applied. This magnetic force will oppose to the force that is being applied. So this is BIL. So we substitute, we have a field of 2.50 Tesla times a current of 1 ampere times a length of 1.20 meters. And that gives you a force that is equal to 3 newtons. And then finally, they say, what is the instantaneous power delivered on the moving bar? Well, in this case, to calculate the power on the moving bar, or the power due to the force, the applied force, we can say that this is equal to the product of the force times its velocity, or its speed. So it's the force, that is going to be 3 newtons, because the force applied will be equal to the force magnetic, so it will be 3 newtons times the speed that we found, right? That was 2 meters per second. And then this would be joules per second. So watts, it would be 6.00 watts. It makes sense, right? That the power delivered by the force in the moving bar be equal to the power that is delivered to the resistor. So both powers are 6 watts, right?